All right, we keep raising the bar. So next speaker is Surya Ganguly, who is a professor of applied physics at Stanford, and he's affiliated with many other departments at Stanford and with Andreessen Horowitz. So he is very well known for his work in taking very complex things like neural networks, LLMs, breaking them down into very small, digestible pieces and analyzing them very thoroughly. And I've been a fan ever since the linear neural network paper that you've had.
Okay, thanks. So this is where we take the bar and we lower it. All right. But actually, by the way, before I say that, a funny thing happened to me on the way to Michigan. My wife actually just bought a company in Michigan near Ann Arbor, so I'll actually be living in Ann Arbor for about a month between mid-June to mid-July. So please do reach out if you want to discuss science. If you want to set up play dates for your kids, I have a 10-year-old and a 3-year-old. So anyway, happy to hang out. Okay. So theories of creativity and reasoning in generative AI. This is a great setup from the two previous speakers. So creativity and reasoning are two capabilities that have long been thought to lie at the apex of human intellectual achievement, right? We admire people who are creative like Dali and who can reason like Andrew Wiles. What's quite surprising and somewhat maybe even disturbing is that creativity and reasoning are starting to be co-opted by machines, right? So here are examples of diffusion model generated images, and they seem to be somewhat creative. These diffusion models also work in other domains like proteins, drugs, robot policies, language, and so forth. And so one wonders, where are these things coming from? How are they related to the training data? How is it turning the training data into these new images? In what sense is it creative? How is that creativity coming about? And also in mathematical reasoning, these systems are so good that they can almost obtain gold medals in the International Math Olympiad. But these are no longer just LLMs. They're interacting with explicit reasoning systems like proof checkers and so forth. So how do these work and how do we make them better? So I'm just going to tell you two stories in this talk, two very recent stories from my lab. One is understanding the origins of creativity in diffusion models, and the other is mathematical reasoning. How do large language models find proofs, and how can we improve this capability? Okay, so the first story is done with a great graduate student, Mason Kam, in my lab. And so again, these are the creative images that we're going to try to understand. The first paper on diffusion models was done by Joshua Soldikstein in my lab. We were thinking about non-equilibrium system mechanics at the time, and thinking about proofs like of the Jarzynski equality, which involved looking at log probability ratios between forward paths and backward paths in the physical world. And we thought maybe we could replace the backward path with a neural network, and Joshua got this to work. Okay? So how do diffusion models work? You have a forward diffusion process that takes data and turns it into noise. And then you train a neural network to reverse this process, and you get a trained reverse process, which, if it works, can take noise and turn it into structured data. Okay? But there's a puzzle about this, is why does it even work in the first place, right? So if you think about what's happening, you can show that these diffusion models, if they work perfectly, they'll never be able to be creative. So if you think about the forward process starting from a finite data distribution, here, say, for example, 3 training points in image space, so 3 images, for example, and you undergo forward diffusion, so the time-dependent probability distribution is the convolution of an ever-expanding Gaussian kernel with these points. So initially you get a mixture of Gaussians, and then they coalesce. Okay, and then let's say you want to learn the reverse process. You can show that you can analytically write down the reverse process, okay, using the score function. So what is a score function? It's the gradient of the log probability in image space of these time-dependent probability distributions. So it's a little vector field or force field. Physicists would call this a force. Statisticians call it a score. I don't know why. But it's a force field that pushes you up the probability gradient. And so it's sort of clear, if you sample from a Gaussian and you keep following this gradient, you have to end up at a training set point. There's nothing else that can happen. So that's a mathematical fact. This means that, and now a lot of these diffusion models are trained to learn this score function, okay? So this tells you that if neural networks succeed at what they're trained to do, to learn the perfect score function, they cannot be creative. So their creativity lies in their failure to be able to do the very thing they're trained to do. But then if they fail, how do they fail in interesting and useful ways to achieve this creativity? Okay, so this is, I kind of explained this intuitively, but this has also been pointed out, for example, in this paper and other papers, this puzzle. Okay, I'm going to tell you the answer and the take-home messages first, and then I'll substantiate them. The key idea is that the neural networks that are implementing this reverse diffusion process are not infinitely expressive. They're these convolutional architectures, like these UNet architectures. And they have two key inductive biases. One is locality. The score computed at a certain pixel location only depends on roughly on its neighbors. And translation equivariance. The score computation, if you translate the image, the score is translated. Right? So in this setting, the basic idea is under the reverse diffusion process, each local patch of the image undergoes reverse diffusion under the ideal score function. Therefore, each patch alone would become close to the patch of one training set point. But now different patches can go to different training set points. And global consistency arises from patch overlaps, and creativity arises from mixing and matching different training example patches in different locations. We derive this theory, which I've only explained in words so far, by writing down the optimal score function subject to the two constraints of locality and translation equivariance. And then we get a set of differential equations that implement that. So again, in pictures, what happens is the perfect reverse diffusion, or the ideal score function, would take the entire image and have it flow back to one of the training set images in the stack here. But the local equivariant score function will have one local patch flow to some training set patch from some location, and another a local patch of the image under reverse diffusion would flow to some other training set patch from another location. Okay? That's what our differential equations do. So how good are these differential equations in predicting the outputs of trained diffusion models? The answer, even surprisingly to us, is that they're remarkably good. So what you're looking at here are pairs of images. The right-hand pair is experiment, the left-hand pair is theory. How do we get them? So we train a diffusion model, either based on a UNet or a ResNet, and we feed some noise into the trained model and we get an image. Then we take that same noise realization and feed it into our theory, and that's what we get on the image on the left pair. And you can see there's a very nice correspondence between theory and experiment. These things are creative, like they're not exactly digits, say for MNIST. And there's a very high quantitative match between theory and experiment with a correlation coefficient of 0.8 to 0.95, depending on the architecture and data set. And I should say importantly that we're only looking at convolutional diffusion models here. More sophisticated diffusion models that have transformer layers break the locality, and they're actually required for modeling more complicated data sets. Okay? That's why we're looking at these simple data sets in this work, because we're not looking at transformer-based architectures, but I'll say a little bit about them at the end of the talk. Okay, so we've shown you, in pictures at least, that the full score machine will converge to a training set point. But now if this local equivariant score machine doesn't converge to training set points, what does it converge to? Right? So we characterize that. So again, here's the score function, and you can think about the local equivariant optimal score function as follows in this equation. So remember, this score function is trying to reverse the forward diffusion process under the constraints of locality and equivariance. So that reversal can be interpreted as a Bayesian guessing game. Each local patch has to guess where it came from in the forward diffusion process. So it has to guess which local image patch in the training process it came from. Right? So in order to optimally guess that, it forms this posterior distribution where, let's say, x of t is a particular local training set, is a local patch that's undergoing the reverse flow. This local patch forms a posterior distribution over all possible training set patches at any possible image location. And that's its optimal posterior, computed where the prior comes from the forward diffusion process. Then it flows towards that patch driven by this force, right? So now obviously this posterior will be larger the closer x of t is to a training set patch in image space. So this dynamics has an intrinsic positive feedback in stability, right? As x of t comes closer to a particular training set patch, the posterior probability that it came from that patch under the forward diffusion process increases. But as that increases, the force driving x of t to that patch also increases. So there's this positive kind of instability amongst all the patches. And due to such instabilities, this posterior probability concentrates on a single training set patch as time t goes to 0, okay, under the reverse diffusion process. Okay, so this allows us to prove a theorem which characterizes the convergence. For every local image patch in the training, under the reverse diffusion, the central pixel of that patch will be equal to the central pixel of the closest training set patch to x0, and this is true across all pixels in the image. So now to illustrate, I think, what is the simplest example of creativity, imagine a training set where you just have 2 images, that's it. So an all black image and an all white image. So if you train a highly expressive diffusion model on these 2 images, it'll memorize the training set and only create those 2 images. But if you imagine what the optimal local equivariant score machine that's kind of handicapped by locality does, let's say with a 3x3 locality patch, right? It creates these new samples, and the consistency condition is equivalent to the following fact. If you look at every 3x3 patch, its central pixel is equal to the majority color of all the pixels in the patch. So for example, this patch clearly came from this image, this patch clearly came from this image, and this patch is a mosaic of the 2 patches, but its central pixel equals a majority color of all the pixels, which is white, okay? So that kind of demarcates the nature of creativity in this model. These are novel, in the language of Lovestock, these are novel. They have some kind of utility in the sense that they match the statistics of the training data, and they're far from the training data, okay? All right, I'll skip that part. Okay, so, but we need to dive a little bit deeper into explaining how we got the theory experiment match, okay? So I didn't actually tell you what spatial scale of locality we chose to match the behavior of the UNet and the ResNet, right? Because that's not determined by our theory, so we have to calibrate the locality scale to the network, right? And we found something quite interesting in that process, right? So it turns out that if you look at the reverse diffusion process, so time t equals 1 is the end of the forward diffusion process and the beginning of the reverse diffusion process, and then you flow backwards in time like this, you can measure the Jacobian of the score computed to the central pixel to all the input pixels and take its absolute value, and this gives you roughly the receptive field of which pixels the score at the central pixel is sensitive to. And you can see that this receptive field or locality scale is quite large early in the reverse diffusion process, and it starts to shrink as you get later and later into the reverse diffusion process. This is for the UNet, this is for the ResNet. And so what we did is we just measured this spatial locality scale, and we just took these numbers, and in our equivariant local score theory, we just put those numbers in as the choice of the spatial locality scale, and we had to make it time dependent, okay? It's actually kind of interesting. I think this is actually a very important observation because suddenly diffusion models allowed us to sample seemingly complex distributions over high dimensional spaces. I mean, that's still a kind of a puzzle as to why it does that and what sample complexity is required to do that. I think this coarse-defined differentiation of structure is key to achieving low sample complexity in order to learn complex distributions over high-dimensional spaces. But that's, I think, future theoretical work. But this is right now an empirical phenomenon that we see in these models. Okay, so we use that to get the theory experiment match that I showed you earlier. But this actually solves a small mystery, which is diffusion models are notorious for creating these crazy-looking images with weird twisted fingers, maybe 10 fingers, 6 fingers, 5's right, but 6 or 7 fingers. Why is that happening? Well, in the fashion MNIST data set, it does that too. For example, it creates pants with 3 legs, shoes with 2 sets of toe regions, shirts with 3 arms, and so forth. That's what the trained diffusion model does. But our theory, it matches what the trained diffusion model does, and it creates the same exact errors. But now we have an explainable theory, so we can explain why that happens. And the key reason is excessive locality at late times in the reverse diffusion process. So as time reverses in the reverse diffusion process, the locality scale is quite small, as you can see from here, a few pixels. So when these final arms are being formed, the region that's deciding to become an arm is deciding to become an arm independent of any other region that's deciding to become an arm. So the reverse diffusion process doesn't enforce global constraints. It can't, because its locality scale is too small. And that explains why this is happening. So this at least diagnoses the problem that the diffusion model doesn't understand global constraints late in the process when the arms appear and the legs appear and so forth. Okay, here are more results on CFAR10, the most complicated data set we looked at. You can see that there's a good match between theory and experiment, but the samples themselves are not that great. Although they do look like the samples that Joshua and I had back in 2015. But you could ask, what if you threw a more complicated diffusion model at CFAR10, especially with transformers that break non-locality? Does our local theory have anything to say about the non-local diffusion model with the transformer layers? Surprisingly, they're actually somewhat related and different in an interesting way. So what we did is we just took an off-the-shelf trained diffusion model based on transformers, and we sampled images from that model in the top row. Then without any modification to our theory, we just took the same noise inputs in the top row and fed them into our theory and got these images in the bottom row. And what you can see is that these images look like a textured patch mosaic. But what happens is the transformer-based diffusion model carves out a more semantically coherent object out of the textured patch mosaic. So for example, here's a rough texture-like looking thing of a bunny. Here's a more coherent bunny where the foreground and background are better separated. Here's a kind of a texture of a cat, a more semantically coherent cat. A texture of a horse, a more semantically coherent horse, and so forth. So it seems like that might be the role of what the transformer layers are doing. They're imposing some kind of semantic coherence on the convolutional backbone that generates textures. But again, there's more work to do there to sort that out. Okay, I will skip the summary. I think it's sort of clear. Okay. So now let's move on to reasoning. In some sense, creativity and reasoning are dual to each other. In creativity, there's no one right answer. But in reasoning, especially in finding a proof or solving a math problem, there is a correct answer. There might be creativity in how you get there, but there can be no ambiguity in the correctness of your proof. So it's kind of a dual problem in that sense. So it's more of like a search problem, a verifiable search problem, and that's how we think about it. So what's happening nowadays with these large language models that are doing math? I think Sean talked a lot about this on the first and second days. So you have a large language model, and you initially pre-train it on the internet, then you fine-tune it maybe on a math data set, and so now it can guess the next step in a proof, but it's not a great guesser. So what you can do is you can feed it to a proof assistant verifier that will take the theorem, the proof so far, and the next guess, and it'll say, is it a valid extension of the proof? And then it can return that information to the large language model, and the large language model can do what it wants with it. If it's valid, it can keep going. If it's invalid, it could backtrack, it could restart, or whatnot. Right? So there's this kind of interactive search process between the large language model and the proof assistant verifier. There's kind of an analogy to human thought where, I mean, if you're familiar with Kahneman's work, this is like our system one, our fast intuition, and this is like system two, which is deliberative, slow, deductive thought. Right? I actually think this analogy is kind of interesting. But in any case, this opens up a new dimension of scaling, which is by scaling up inference time compute via search. So a very simple way to use this proof assistant verifier is to keep going until you get an invalid proof or a successful proof. But then if you get an invalid proof, restart and try again. So then you get the number of tries as a way to scale up the test time compute. And so this horizontal axis is the number of tries. This is the probability of being correct in solving various math problems if you have k tries, right? And you can see that the probability of at least one of your tries being correct scales up with the number of times you guess. So this is great. This is this new knob that we can play with to throw compute in the problem and hopefully do better. Okay. So, but there's a problem with aligning learning and search. Okay. So the learning phase is done by training an LLM to do next token prediction. But the search phase is done by taking multiple potentially parallel guesses along a big search tree. Okay? The problem is learning and inference or search are not co-designed, and therefore this cascading of them can be highly suboptimal. The way to understand this is that learning is maximum likelihood estimation through, say, for next token prediction. So it likes to place as much of the probability as possible on the most likely next steps that are in your training data. Okay? This would be, so its guess distribution, its distribution over next steps in a proof, has quite low entropy, right? This is perfectly fine if it's correct, right? But it could be wrong. So in some sense, learning, in the way we're doing it right now, induces highly confident but incorrect guessers. We may have all had the pleasure of working with colleagues who are confident and wrong. It's not great, but we know that no matter how much you would let a confident wrong guesser guess, it won't give you suddenly a good answer, right? In search, if you know that you have lots of guesses, the best strategy is to hedge your bets and spread your probability across many promising next steps. Even if you're not confident or don't assign high probability to each of your next steps, you know that you have many guesses, so you want to spread your probability. So they kind of have opposing desiderata, right? In fact, learning can hurt search if learning and search are not aligned via co-design. We had numerical experiments to show that this is true. It's in the paper, but I'll skip the details of that. But what can you, oh, and this is the paper, by the way. So again, a great set of grad students, Feng Cheng and Alan Raventos. We were able to prove some theorems and find a new algorithm that helps with this lack of alignment between learning and search. The theorem, informally stated, is the following. So let's say you have a guesser that has a given accuracy constraint. So it can't be, it's not a perfect guesser, it has some probability of error in its guessing. And under the constraint of being allowed n guesses at test time, the optimal guessing policy obeys the following properties. If you're not allowed that many guesses at search time, small n where n is the number of guesses, the optimal guesser should confidently exploit a low entropy guess distribution. So it puts all its eggs in the few guesses that it can have. On the other hand, if you're allowed many guesses at search time or inference time, the optimal guesser should unconfidently explore a high entropy guess distribution. Again, it should spread its guesses around. So there's a formal statement of this theorem that we proved in the paper. And then we discovered an efficient algorithm that chooses the right amount of exploration for any amount of n searches at test time. And the basic idea is, don't maximize the probability of being correct in one guess, maximize the probability of being correct in n guesses, and you can make that efficient. So we replace pre-training with this novel cost function or objective. And then these are the results. Okay, so there's a bit of a lot of stuff on this graph, so let me spell it out. Okay, so this horizontal axis is the test time compute, the number of guesses that we allow ourselves at test time. The task is to find mathematical proofs and solve math problems. We learned and trained an 8 billion parameter language model with various different levels of exploration. So this n prime is a hyperparameter, which is how much exploration we allow or encourage during the learning phase, okay? So n prime is a hyperparameter used for learning. N prime equals 1 is just maximum likelihood estimation, or minimizing cross-entropy loss. So that's this red curve. And you can see that this is, and coverage is just the probability of being correct in n guesses. So you can see that you do slightly better with the way that everybody else does it if you allow n guesses. But these curves of different colors are what you get if you change the cross-entropy loss function to our loss function that encourages more exploration. And you can see that at different amounts of test time search, there are different amounts of training time exploration that you'd like to encourage. And the Pareto frontier is of course the highest thing you can get. And you achieve the Pareto frontier by matching the exploration used during learning, the n prime, with the n used at test time. Right? So it shows that you really need to co-design learning and search to achieve the Pareto frontier. Okay? And that's basically it. So this teaches us, in various areas of machine learning and signal processing, we have these separation theorems, right? Shannon taught us that we can do source coding independently of channel coding, and we cascade them and we still achieve optimality. In linear control theory, you can do state estimation and controller design independently, and you'll still be fine. Here, learning and search cannot be independent of each other. They have to be co-designed. So these two phases of the foundation model creation process that are traditionally not talking to each other, I think they do have to talk to each other better. And you can imagine there's all sorts of ways to do the co-design depending on the sophistication of the test time compute strategy. So there's a lot of research to do here, I think. And I'm in trouble now, so
No. I mean, keep going.
I will stop.
But not for too long.
There's a lot of stuff I didn't talk about. Like I also do a lot of work in computational neuroscience and all that stuff. If you're interested, I actually recently gave a TED talk where I talked about major order of magnitude discrepancies between brains and machines in terms of the data efficiency, and these are order of magnitude discrepancies. Data efficiency, energy efficiency, how we can go beyond evolution to build quantum neuromorphic hardware, explainable AI, and actually melding minds and machines where you can bidirectionally couple AI systems to brains, at least in mice, where you can read and write. You can read from the mouse, apply control theory to the machine, and then discover control signals you can inject in the mouse to make the mouse do things, right? So there's really cool stuff going on at the interface of neuroscience and AI. But if you're interested, you can look at this talk, and I'll stop here. Thanks.
Great, thank you very much. I have to call up the president to say where the bar is right now, because I don't have the words. Somebody has the words. All right. Okay, so again, really fascinating on many ends. And I know I'm taxing you on 2 panels, but given this slide, I might have to put you on the 3rd panel as well, like this afternoon. But I might spare you on that. Okay, so because we're again out of time, I'll just ask one question, or it's more like a comment from the audience. So Todd, so he says, is a local issue in the diffusion model tied to training getting stuck in the local minima during training? Because each local patch would have its own local minima to get stuck in, and this then builds up into emergence, creativity, guessing, things like that.
Yeah. So there's local minima in the loss function for learning the score, and then there's the multiple fixed points of the dynamical system. So I don't think they're related in any simple way, because the local minima of the loss function are critical points of a landscape, but the reverse diffusion process is not doing any kind of gradient descent on any landscape. It's a dynamical system that probably doesn't have a Lyapunov function, but it does have multiple fixed points. So it's true that the reverse dynamics have multiple fixed points, but I don't think that's related to local minimum in the loss landscape, but the score function over the weights of a network.
Okay. So I have a quick question. So is there anything at all you can learn from a linear diffusion model? You basically parameterize the score function as AX plus B.
We played that game. It basically does like PCA.
Interesting.
We haven't fully worked it out because we didn't think the results would be super interesting, but just initial results, it's kind of doing.
But if you're not learning A and B correctly, and you're maybe using SGD or something to get. I think there may be some interesting dynamics.
What I would love is actually a theory of the sample complexity of such a system, and that's where we want to look at the linear system.
You said you're here for the next month?
I'm here for the next month,
Let's
so
try
happy
to do
chat.
something.
All
right, thank you so much again. So we go on a short break, and then we're back with 5 amazing people for the next panel on the same topic of this morning. Thank you very much. Thank you to the speakers.